All right, guys, so it is time for a quick conversation about Faraday's Law, and that will finish up our unit on thermochemistry and electrochemistry, which means we will finish content for AP Chemistry for the year. And then it's testing and review and preparing for our exam. So let's jump right in to a discussion of Faraday's Law. So this is really continuing our conversation about electrochemical cells. And so Faraday's Law just says that the amount of substance produced or consumed at each electrode is directly proportional to the quantity of charge that flows through the cell. And what this does is it allows us to connect the stoichiometry that we've been using in all of chemistry to electrical measurements, current and charge. So first, let's talk about current. Current is defined as the charge per unit time. And so for our purposes, we'll always use current in amperes. So we will be measuring coulombs per second. And a coulomb per second is an ampere or an amp. And you guys are probably familiar with an amp because this is the way a lot of circuits are rated in homes. The other term that we'll be using in this section is a Faraday, from the same guy that we get the name of the law. And a Faraday is simply the charge on a mole of electrons. So it's 96,485 coulombs. And that's derived from the charge per electron times the number of electrons per mole. And that's how we get the 96,485. You'll also see 96,500 used here. It really just depends on how many significant figures you want. But it's important to remember that a Faraday is a mole of electrons. And this equation for current, I equals Q over T, where I is current, Q is charge, and T is time in seconds, is on your equations and constants sheet, as is the number for the Faraday. Okay, so how do we apply this? Well, questions typically look like this. What current would be required to produce 4.25 grams of copper in an hour in a standard copper zinc cell? So this is really just a stoichiometry problem, but before we can do our stoichiometry problem, of course, we need a balanced chemical equation. So we're going to write our copper half reaction. The copper ions are receiving 2 electrons and forming solid copper. And the zinc is dissolving into zinc ions and electrons. So we're going to set this up like we would any other stoichiometry problem. We're going to start out with our 4.25 grams of copper. We're going to divide that by the molar mass of copper to convert to moles of copper. Then we're going to convert from moles of copper to moles of electrons. And since 2 electrons are transferred, we want to make sure we use 2 moles of electrons per mole of copper. And now we need to convert from moles of electrons. So we're going to use the Faraday. So 1 mole of electrons is 96,485 coulombs. And now we can convert our hour that we started out with, since we had an hour, to seconds. And so we are going to use 1 hour is 3,600 seconds. And now you can see that what we have left is coulombs per second, which is the same thing as an amp. And so the current that we would need is 3.58 amps. Again, just a new application of stoichiometry. You can expect to see problems like this as multiple choice problems, but you wouldn't actually have to solve the question. You would just need to set it up. And we'll look at some examples of those in class. Okay, applying Faraday's law. Here's a new application. We're being asked to find if we have an electrolytic cell. So we're electroplating gold onto a surface. What mass of gold can be electroplated when we pass 0.25 Faradays of charge through a solution of gold to sulfate? So we're going to write our gold reduction so that we know how many moles of electrons. And then we're going to start out with our 0.25 Faradays. We know that 1 Faraday is 1 mole of electrons. So notice that we have a slightly different application here. Rather than converting from moles of electrons to coulombs, we're converting from Faradays to moles of electrons. So that allows us to cancel out the Faraday. And then we know that for every 1 mole of gold, we have 2 moles of electrons. We cancel out the moles of electrons. And now we just need the mass of gold. So we'll use the molar mass of gold, and we'll be able to cancel out moles. And we find that by passing 1/4 of a Faraday of charge, we can generate 25 grams of gold from our solution. Okay, and one more practice problem. Again, these are common questions. How many seconds will it take to plate out 5 grams of silver from a solution of silver nitrate using a 20 amp current? So we have our reduction reaction. Silver ions plus 1 electron makes solid silver. We'll start with our 5 grams of silver, and we're going to convert that to moles of silver using the molar mass. And then we'll convert from moles of silver to moles of electrons. And since this is 1-to-1, that's an easy calculation. And now we need to convert from moles of electrons to coulombs. So we're going to use that Faraday constant, 96,485 coulombs per mole of electrons. And then we're going to use the fact that our current is 20 coulombs per second, because an ampere is a coulomb per second. And so we can use 20 coulombs per second here to cancel out our coulombs. And we get that it will take us 220 seconds. So not very long. Okay, that's it. Pretty simple and straightforward. As always, if you have any questions, let me know.